This video shows you how to predict the mass spectrum of diatomic bromine, including how to predict the mass to charge values and the relative intensities of the molecular ion peaks you get. This is particularly relevant for the AQA syllabus, where questions have been asked for you to actually sketch one of the mass spectrum you would obtain from a diatomic molecule. Okay, if we look at the element bromine, it exists as two isotopes, bromine 79 and bromine 81. If you had a sample of that, you would find that 50% of the atoms are actually bromine 79 and roughly the other 50% of the atoms are bromine 81. So these isotopes exist in a 1-to-1 ratio. This helps us because bromine being a diatomic molecule, we have got those two bromine atoms in there linked by a covalent bond. When we do electron impact ionisation, we get a high energy electron being emitted from an electron gun which hits the molecule. Two things can actually happen to that. The first one is that the high energy electron will break that covalent bond between the atoms and leave us with some positively charged bromine ions. The other thing that can happen is that it just knocks off an electron, leaving the bromine molecule still behind as a diatomic molecule with a positive charge on it. First thing to do then is to actually sketch those two lines onto your mass spectrum. So the first line at 79 will be our 79Br+, second line will be the 81Br+. Again, those heights of the peaks should be in a 1-to-1 ratio because the two isotopes exist in a 1-to-1 ratio normally in nature. It doesn't matter on the height of the peaks in terms of the percentage abundance as long as they are in a 1-to-1 ratio. We then have to consider the molecular ion peaks. So we can have the following combinations of isotopes. So if our molecular ion is a combination of two bromine 79s, we will get a mass to charge peak at 158. We can then have the first atom being a 79 and the second atom being an 81Br, or we can have the opposite way around, the first atom in the molecule being 81 and the second being 79. Both of these cases will give us a mass to charge of 160. We can then just have both the atoms in there being bromine 81 to give us a mass to charge of 162. Now we need to be able to predict the relative heights of the peaks. This is where we have to bring in a little bit of probability. To do this, we have to consider the probability of the first atom in the molecule being, for instance, bromine 79. So it's a sample of bromine, this is 50%, this is a half. We then consider the probability of the second atom in the molecule also being bromine 79, that's also 50% or 1/2. To get the total probability involved in the combination of 79 to 79, we've got to multiply those two probabilities together to give us the total for that combination. So the table here then shows us the mass to charge and the molecular ion. We've just got to calculate the probability of that combination. So for mass to charge 158, that's the combination of two lots of bromine 79. We have 1/2 times 1/2 giving us a quarter. Now for mass to charge 160, we have got two possible combinations. The first possibility is a bromine 79 as the first atom and a bromine 81 as the second atom. The other possibility is bromine 81 as the first atom and bromine 79 as the second atom in that molecule. So we have to add together the individual probabilities for that one. So for the first combination, 79-81, we have 1/2 times 1/2 giving us a quarter, and for the 81-79 combination we've also got 1/2 times 1/2 giving us a quarter. Now if we total that up, that gives us a probability of 1/2 in total. For the 162 molecular ion peak of two lots of 81, again we've got 1/2 times 1/2 giving us a quarter. So if we actually look at the relative intensities of this, we have got a 1 to 2 to 1 on our molecular ion peaks. Okay, and this is reflected in the mass spectrum. Okay, so now we can start putting the rest of our molecular ion peaks on the sketch. So we've already got the two peaks corresponding to the 79Br+ and the 81Br+ ion. We're now going to add the peak at 158 from the two 79Brs. We've got a peak then at 160 for the 79-81 and the 81-79 combinations, and we've got the peak at 162 for the two bromine 81s. Again, we've just calculated they're in a 1 to 2 to 1 ratio, but just watch out, the total of the molecular ion peak sort of abundances should add up to 100%, so ideally these should be in a 25 to 50 to 25% ratio. There is another way to check the relative intensities for the molecular ion peaks. That's if we actually list the atoms in the molecule. So we've got the first column showing the first atom in the molecule, the second column shows the second atom in the molecule. If we actually look at the combinations we can have, there's one possibility of a 79 to 79. There's actually two possibilities of having a 79 and an 81 combined. And there's one possibility then of two lots of 81Br coming together. So again, this shows us we have a 1 to 2 to 1 ratio for our molecular ion peaks. Just to finish off then, here's an exam style question. Bromine exists as two isotopes, bromine 79 and bromine 81, in the ratio 1 to 1. Which statement about the peaks in the mass spectrum of bromine is correct? Now for A, unfortunately, if you actually work out the peaks you're going to get for the molecular ion, we have 160 missing, which is a combination of bromine 79 and 81. So it can't be A. For B, again, we've got another common mistake. For the mass charge peak at 160, what students tend to do is forget you've actually got two possible combinations, with the first atom being 79 and the second atom being 81, or the opposite, with the first atom being 81 and the second being 79. So they forget to add the probabilities together to give you a ratio of 1 to 2 to 1. So the correct answer on here, again, D is missing the mass charge peak at 160, is in fact C.